Welcome to the deep dive. Today we're tackling, well, a really fascinating question about probability. Imagine this. You flip a fair coin. Not once, not twice, but 5 million times.
Yeah.
A huge number. So here's the core question for you. Is getting exactly one tail in all those flips just as likely as getting, say, exactly half tails and half heads, 2.5 million tails? I mean, your first reaction might be, no way, right? But how big is that difference? And why is it so big? It gets pretty mind-bending.
It really does. It's a great question because it pushes past our everyday intuition about chance. Each coin flip, totally independent. The coin doesn't remember what came before. But when you look at millions of flips together, these statistical patterns emerge that show this, well, almost unbelievable difference in likelihoods. It's like order just appearing out of randomness.
Okay, order from randomness. I like that. So individual flips are random, but the collection behaves predictably. How does that work? Is it about how we define the outcome?
Exactly. That's the absolute key insight here. We need to be clear about a specific sequence versus an overall outcome. Think about any single exact sequence of 5 million flips. Maybe it's tail, then all heads. Or head, tail, all the way down. Any one specific sequence you can name has the exact same probability, which is incredibly tiny. It's basically 0.5 multiplied by itself 5 million times.
Right, 0.5 to the power of 5,000. Effectively, zero chance for any one specific lineup. So if every sequence is equally improbable, the difference has to come from counting how many sequences give you a certain result, like one tail.
Precisely. That's where the maths, specifically the binomial distribution, comes into play. It's the tool we use. An outcome like one tail isn't just one sequence. It's a whole set of sequences. We're not just looking at the probability of one path, but the number of paths that lead to that same end result.
The number of ways. Okay, that makes sense. So for the one-tail outcome, well, that seems straightforward enough. The tail could be the first flip, or the second, or the third, all the way to the 5 millionth flip. So 5 million ways, right?
Exactly. 5 million possible sequences result in exactly one tail. Simple enough. But now think about the half and half outcome. 2.5 million tails and 2.5 million heads. The number of ways that can happen, it's calculated using combinations, factorials, and the number is just astronomically larger. Forget trying it on a calculator.
Astronomically larger. Yeah, I can imagine. So how on earth do we even compare these? How do we calculate that?
Well, we need some pretty powerful mathematical tools. Things like Stirling's approximation. It lets us estimate these massive factorials really accurately. And when you run the numbers, the probability of getting exactly one tail, it comes out to roughly 5 times 10 to the power of negative 1.5 million, almost. So imagine a decimal point, then almost 1.5 million zeros before you even get to the digit 5.
Wow. Okay, that's basically zero.
Yeah.
And the probability exactly half and half, the 2.5 million tails?
That one, the most central outcome, is much, much higher in comparison. It's approximately 0.00003568. Still small, maybe, but compared to the other.
It's not even close. You're saying the half and half outcome is more likely by a factor of something like 10 to the power of 1.5 million.
Yeah.
I can't even picture that number. It's beyond physical meaning, like you said.
It really is. And it's not just some weird mathematical quirk. This huge difference is showing us something fundamental. It's a consequence of things like the law of large numbers, which, basically says that the more times you repeat an experiment, like flipping a coin, the closer your overall results will get to the expected average.
So the system naturally wants to settle towards 50-50.
Okay.
But why is that specific outcome so incredibly dominant over all others?
Right. And that connects to another big idea, the central limit theorem. It tells us that when you add up lots of independent random things, the distribution of the possible sums tends to look like a bell curve. A normal distribution. Think of that curve. The peak, the highest point, is the average outcome. In our case, that's the 50-50 split. Exactly 2.5 million tails. It has a z-score of 0, right in the middle.
Okay, it's at the peak, so where's the one-tail outcome on this curve?
The one-tail outcome, it's so far out in the tail of that bell curve, it's almost unbelievable. We're talking about 2,236 standard deviations away from the mean from that peak. It's basically fallen off the edge of the probability map. Its probability is, for all practical purposes, 0.
So what's the big takeaway here for you listening? It seems like even though single random events, like one coin flip, are unpredictable, when you have millions of them happening, very clear, predictable patterns just emerge, and the most likely outcome isn't just a bit more likely, it's, well, overwhelmingly dominant.
It's a fantastic illustration of microstates versus macrostates. Think of each specific sequence of 5 million flips as a microstate. every single one is equally unlikely. But the overall result, like roughly half heads, that's a macrostate. And the macrostate that can be formed in the most number of ways, the 50-50 split, just swamps everything else. It's how order emerges from randomness in physics, too, like in thermodynamics.
Fascinating.
Mm.
And just to hammer it home, even if you flipped, say, 10 million coins independently, the chance of seeing any of them land, showing exactly one tail out of the 10 million flips, is still practically zero. The scale doesn't make the extreme event likely. Which leads us to a final thought for you to ponder. Where else in our world, in economics, biology, maybe even social trends, might we see seemingly random individual actions adding up in such vast numbers that they're secretly governed by these huge combinatorial forces, leading to predictable large-scale patterns we might not expect, what looks random up close but becomes predictable from afar?